All right, let's get started. Okay, so last week we started learning how to count certain sets, right? Well, not sets, I mean lists, sorry. We learned how to start counting lists. How many ways can we do things? We found out if I'm choosing from n elements, so if I have n elements to choose from, say I have 3 markers to choose from, and I'm going to choose markers 3 times, and I put the marker back after I choose it, how many combinations can I get? 3 times 3 times 3. I have 3 options for my first choice, 3 options for my second choice, 3 options for my third choice. Or 3 to the power of 3. Yeah, when we put it back. Garbage in here? Oh. So 3 times 3 times 3, or 3 to the 3. In general, if we have n objects to choose from, if we have n objects to choose from, and we're going to choose k times, then this is how many ways we can do it with replacement, right? Then we had the other conversation, the one that's probably less intuitive, I don't know, where you don't put it back. That's what we use this n sub k notation for. So if I have n objects to choose from, with no duplicates, and I'm going to choose k times, then this is how many of those lists we can make. You remember that? So the example, one of the examples we used was this one. If we have 10 people together in a club, how many ways can we elect a president, a vice president, a secretary, and a treasurer? Now you could just know in your head, let's see, we have 10 for the first, 9 for the second, 8 for the third, and 7 for the fourth. And that's perfectly fine. Or you could use this formula. This formula says start at 10, we're going to count down until we get to n minus k plus 1. N was 10, k is 4, 10 minus 4 is 6. Good job. 10 minus 4 is 6, plus 1 is 7. So we keep counting down until we get to 7. 10, 9, 8, 7, stop. Both those perfectly valid ways to do it. But we're going to focus on this notation going forward for the next section for factorial. Because then we're going to define n factorial to be n sub n. It's when you have n objects and you're going to choose all n of them. Another way that we think about it is it's an arrangement. So if I have 3 objects and I'm going to choose 3 of them, that's the same as putting 3 objects in an order. I need to pick one to be first, pick one to be second, pick one to be third. How many options do I have for which one goes first? 3. How many options do I have for which one goes second? 2. How many options do I have for which one goes last? 1. So n factorial 3 times 2 times 1, which is exactly what this notation tells you, right? We go from n all the way to n minus n plus 1. Same thing. You with me? Mm-hmm. So do you see how factorial is intuitively counting how many ways we can arrange people? So if I want to know how many ways can I take you guys up and line you up in a row up here, how many ways can we do it? 2, 4, 6 of you? 6 factorial, right? I have 6 options for who's going to go first. Once I pick Laura, I now only have 5 options for who comes second, etc., 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 right? You with me? Factorial counts arrangements. So one way we think about this is how many ways can I take n objects from an n element list, or how many ways can I arrange n objects? Both perfectly valid ways to think about it. So example of 5 factorial, 5 factorial, 5 times 4 times 3 times 2 times 1. Exactly what you expect. You can get it from the formula, or you can just keep counting down until you reach your end, whatever you like. So then the question becomes, what about 0 factorial? What's that going to equal? What do you think 0 factorial equals?
0 times 0 times
0?
1.
1? We got zeros, we got ones?
No, it'd be 0.
No, it'd be 0. So let's think about the question associated with this. How many, not how many 0 element lists can be made from a set with no elements? So I get to choose from no elements. How many lists can I make?
1.
I can make 1, the empty list, the list that doesn't have anything in it.
But then is it even a list that doesn't have anything?
Sure. It's an empty list. Nothing wrong with the list being empty. That's how every grocery list starts. So the answer is 1. 0 factorial is equal to 1. If you'll read the book, the author puts a lot of effort into coming up with different scenarios where you want to use factorial to solve a problem, and then helping you establish that in your intuition that the answer should be 1. Now, most books don't bother trying to make this appeal to your intuition. They don't care about your intuition. They just define it that way. So a typical definition for factorial is right here. Typically, we just say n factorial equals n times n minus 1 factorial, where 0 factorial equals 1. So this is a common textbook definition. The author defines it this way and then handles 0 factorial as a special case to try and appeal to your intuition. But says the same thing. So 0 factorial is 1. Good?
Yeah.
Yeah? All right. Another notation. How many of you are used to summation notation? Just one? So let's write it out. Maybe you've seen it and you just don't remember. So when I do sigma, and I want to add up all the numbers k equals 1 to 7 of k. You've never seen this?
We have.
It's equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7.
Yeah.
So that's what this is saying. It says we start k at 1, and we keep incrementing it, plugging in an increment, over and over again, adding up your results until you reach 7. So this tells us where to start. We start with 1. Okay, so k equals 1, plug it in here. We got 1. Okay, have we reached 7 yet? No, so go back. Now k is 2, plug in 2, add it on. Have we reached 7 yet? No. Continue until you reach 7. Let's do a more convoluted example just to help expand your intuition. What if I said we're going to go from k equals 3 to 7 of k squared minus 1? This is going to be equal to, here's where you start, plug in 3. What do we get when we plug in 3?
3 squared, which is 9.
9 minus 1,
So
8. Plus, have we reached 7 yet? No. No. Has what we plugged in, have we plugged in 7 yet? There's another way to say it. Keep going until you plug in 7. So we plugged in 3, now we plug in 4. 4 squared is 16, minus 1 is 15, plus, now we plug in 5, 25 minus 1 is 24, plus plug in 6, 35, plus plug in 7, 48. And then we stop.
So would the answer be 48 or would it be 8?
No, it's the sum. You need to add it all up. It's just that sometimes when we have to write really big sums, that becomes very tedious, so we come up with this notation for writing really big sums in a really small way. That's what the notation's for.
Okay.
So we also have product notation. It's the same thing. The idea is instead of a sigma, we replace this with a capital pi, and instead of plus, we replace it with a times. But it's the exact same thinking. Okay?
Okay.
So, for example, here's another definition of n factorial. I can define n factorial as the product of all the numbers k starting at 1 going to n. Right?
Yeah.
Does that make sense, or should we draw this out?
No, that makes sense.
Makes sense? Should we draw it out?
Yeah.
Let's draw it out. Okay, so let's look at 5 factorial, for example. 5 factorial, what's that equal to? 5 times 4 times 3 times 2 times 1. So now let's see if that's really equal to the product starting at k equals 1 going to 5 of k. Alright, let's see if we get the same thing. So plug in 1 for k, what do we get? 1. Have we reached 5 yet? Nope, so plug in 2 for k. Then we're going to plug in 3 for k. Then we're going to plug in 4 for k. Then we're going to plug in 5 for k. Ah, yes, it's 5 times 4 times 3 times 2 times 1. Good?
You would just
Yeah.
write that like summation being instead.
Pi.
Yeah.
Product notation, not sum. Product. We're multiplying. So yeah, here's one way to write 5 factorial. Here's another perfectly valid way to write 5 factorial. Here's another perfectly valid way to write 5 factorial. Right? So that's product notation. Let's do some examples to make sure that you're getting it. So tell me what terms to start multiplying together. What's first? 1, then
2,
then
3,
then
4,
then
5,
then
6,
then
7,
then.
No.
Oh, no. Okay, what about this one? What's the first term?
3.
Try again.
2. Wait, is that 2?
We got
2.
19.
19 is the first term.
Wow, we did that.
Plug in 3 for k. Case 3 squared is
9.
9.
times 2 is plus 1 is. All right. What about when we plug in 4?
37.
Almost.
3.
33. Right? 4 squared is 16. 16 times 2 is 11.
No.
No, okay. Make sure you're paying attention. 16 times 2 is,
32.
you know it's just one less than that, right? You don't even have to think about it. Plus 1. Trusting that I got the right answer. All right, times. What happens when we plug in 5?
51.
51. That one's easy, right? And the last one is
73.
73.
Technically, it's not the last one,
It's not. We did 3, 4, 5, 6. We stopped when we reached 6. This is what we got when we plugged in 3. This is what we got when we plugged in 4. This is what we got when we plugged in 5. This is what we got when we
So
plugged
you
in 6.
start at what k equals?
Yes, you start at this number and you end at this number.
So you don't have to do 6 spots. You just have to
Correct.
plug in.
You just have to plug in 3, 4, 5, and 6 when it's 3 to 6.
Okay.
Here we have to plug in 1 to 7.
Okay.
All right, one more weird case. I go from k equals 1 to 0 of k. What do we think?
1.
1.
We got a 0, a 1. Any other answers? Raise your hand if you think 0.
I don't know.
Emma raised her hand.
So we can all raise our hand.
Raise your hand if you think 1.
I have no idea.
And then other people have no idea. Raise your hand if you don't think there is an answer. It's like dividing by 0.
It's 1 times 0.
It's 1 times 0. Almost. That's the same as 0. The answer is 1. How do we know that the answer is 1?
Because of the 0.
0 factorial. This is the same thing as 0 factorial. Remember, we could also define factorial as from 1 to n gives us n factorial. So even though it feels weird that it's defined in this situation, it actually is defined in this situation, as awkward as that feels. Okay? So that's the one gotcha. But once you get past that gotcha, I think everything else is pretty intuitive. You understand how to plug in. That's the only one that's weird, and someone just has to tell you what it is. Okay, that's it for factorial.
Great.
We just finished the section. Let's do one more. Sets. We're going to start with sets now. Intuitively, the way I describe a set is it is a unique, unordered collection. That's what a set is. When you have a set of objects, it doesn't matter what order they're in, and it doesn't matter if you have multiple objects in there, it's still the same set. So in other words, this set and this set are the exact same set. Even though this is in a different order, and even though this one has extra 3's, they're still the exact same set. We don't care about order, we don't care about duplicates, a set. Okay? Now this will follow from what we need for sets to be equal, but that's just to help get your intuition going.
Okay.
So our notation for sets, what's a set? Or what can you put in a set? You can put anything you want in a set. It's just a collection of objects, anything. Doesn't matter. And we just comma separate the objects we're putting in between two brackets. That's how we signify a set. So this is a set containing 1, 2, SpongeBob, and the set 1, 2, 3. Question, how many objects are in this set?
4.
Whoa, 1, 2, 3, 4, 5, 6, right?
No.
No, just 4. 1, 2, 3, 4. Just like with the list, right?
Yeah.
How many objects in there?
3.
Is everything in here in here?
No.
Yeah.
No! There's a 3 in here. There's no 3 in here. There's just a 1, 2, SpongeBob, and a set containing 1, 2, 3.
But doesn't.
So no, there is not a 3 in this set. There's a 3 in this set.
There's a set containing 3 inside the set.
That is correct. There is a set containing 3 inside this set.
So doesn't that mean that there's a 3
This isn't like if I have a word in a book in this room, then the word's in the room. Doesn't work that way.
Yeah.
When we say what's in the set, we mean what are the elements of the set. This set has exactly 4 elements. Those elements are 1, 2, SpongeBob in the set, 1, 2, 3. Good? So that's what we mean by this notation. I don't know if I've already been using it, but this notation, that little epsilon there, means in. So 1 is in the set 1, 2, 3. True or false?
True.
True.
1 is not in the set 2, 3. True or false?
It's true.
True.
Okay.
Okay. 1, 2 is not in the set 1, 2. True or false? False. It's obviously in there, right?
Oh, man.
No! What's in this set? 1's in there. 2's in there. Is the set containing 1, 2 in there? I can't see it. I only see 2 things in here.
Oh, because the set.
The first thing in there's 1. The second thing's in there's 2.
So you're saying.
Neither of those are the set containing 1, 2.
Oh.
This is not in there. Is the set containing 1, 2 in this set?
Yes.
Yes. Okay. You're going to get confused by being in. Once we get to subset, you're going to get confused back and forth between which is which. So, even though I help you with all these corner cases, chances are when you're doing your homework, you're going to make a mistake. So, try and watch out for that. Think, can I find that thing somewhere in there? Okay. So, equality. What do we mean when we say that 2 sets are equal? Sets A and B are equal if and only if every element of A is an element of B, and every element of B is in A. I should have said is an element of A. So if everything in A is in B, and everything in B is in A, then the 2 sets are equal. Okay? So for those of you who like the notation rather than an essay, here's what it is. X in A implies X is in B, and X in B implies X is in A. That's what it means for the sets to be equal. If you like, I know that those of you come from logic probably like that better.
Yeah.
So these 2 sets, are they equal?
Yes.
Okay.
Yeah, I already told you that they are, but now let's think with the definition. They're only equal if everything in here is in here, and everything in here is in here. Are they equal?
Yes.
Yeah. Pick any element you want in here, 1, 2, or 3, or 3, and it's also in here. Pick any element you want in here, and it's also in here. Therefore, the sets are equal. Okay, so we've been kind of loosely talking about the size of a set. When we're talking about the size of the set, how many elements are in the set, we're talking about its cardinality. So the cardinality of a set A, we write it like this, the absolute value of A, kind of. That means the size of the set, or the cardinality of the set. So the cardinality of a set A is the number of elements in it. Right? What's the cardinality of this set?
4.
4. What's the cardinality of this set?
3.
This set?
2.
This set?
2.
3. 2. Good job. It's 2, not 3. Wonderful. So, we also have a definition now of finite. So let's read it. If the cardinality of a set A is an integer, then we say that A is a finite set. If I can find some integer that gives me the count of the set, if I can find an integer that tells me how many elements are in the set, then the set is finite. Or in other words, there's not infinitely many of them, right? Because infinity is not an integer, right? It's irrational. All right. So, example. What's the cardinality of this set?
3.
3. What's the cardinality of this set?
2.
2. Good. So, any questions about what we've covered so far? Okay. Some notation. We call this set builder notation. So, oftentimes, rather than listing out all the elements in the set, we just want to tell you some pattern that the elements are going to follow that we're listing. You've done this with functions all the time. So when you want to talk about a function, sometimes you just say f of x is equal to x squared, maybe. And this is representing an infinite number of points. And sometimes you plot all those points on a graph, right? But this is representing an infinite number of points. Sometimes you want to do something similar with a set. You want to talk about a set that has an infinite number of objects in it. So how are you going to say that? Here's one way that you can do it. We do it with set builder notation. You have what's called a dummy variable and then some condition involving that dummy variable. So for example, say I want to talk about the set of all the even numbers. How can I do that? I can say that that's the set of all x. X is my dummy variable. Such that is the way that we read that colon, or where such that. So evens equals the set of all x such that x is an integer and 2 divides x. Now sometimes, right after we do the such that part, we say that it's in another set. So when that's the case, when it's x such that x is an integer and something, then sometimes we just say it's the set of all integers such that 2 divides x. So both these are the exact same. Another example, what if we want to define all the integers? We can say the set of integers is not integers, naturals. Thank you, naturals. The set of naturals is equal to all integers that are greater than or equal to 0. It's a set of all integers x such that x is greater than or equal to 0, right? The natural numbers are all the positive integers, including 0. That's what the naturals are. Is that making sense?
Yes.
Okay. Proving two sets are equal. So now we're going to do a quick proof showing that two sets are equal. Now, well, let's go over the two sets and then we'll talk about how I'm going to show that they're equal. So the set of all evens and the set of all integers that can be expressed as the sum of two odds. That's what these sets are.
First
So,
set is evens.
yeah, this one's a set of all evens. The set of all integers such that 2 divides x. The set of all integers x such that 2 divides x. That's the set of all evens. And the set of all z, where z is equal to a plus b, where a and b are both odd. Or in other words, this set is a set of all the integers that can be expressed as a sum of two odd numbers. So we're going to show that the set of evens and the set of integers that can be expressed as a sum of two odd numbers are the same set. If it can be expressed as a sum of two odd numbers, it's even. If it's even, it can be expressed as a sum of two odd numbers. Therefore, the sets are even. How do we do that? We're going to grab something out of this set. We're going to grab an arbitrary element out of this set and show it's in this set. And then we're going to grab an arbitrary element out of this set and show it's in this set. If everything in here is in here, and everything in here is in here, then they're the same set. You with me? So the way that we're going to start this, let A, just to name the sets, let A be the set of all evens, and let B be the set of all integers that can be expressed as a sum of two odds. With me? And then we'll fill in from here. So first thing I'm going to do is grab something. I don't know which way we want to show it first. Should we show A is a subset of B, or sorry, should we show that everything in A is in B, or should we show that everything in B is in A first?
Everything that B is in
Let's do it. Okay, so we'll grab something out of B first. So pick some random thing out of B. Let X be anything in B. Doesn't matter. We're going to show that it's also in A. Okay?
Wait, you're already using X.
That's just a dummy variable. The X here has nothing to do with the X's up here. But if that's going to confuse you, we can grab N. Grab N out of B. Grab anything you want out of B. Just something. We're going to call it N. If it's in B, what do we know?
There's two integers.
Yeah, that there's two integers such that their sum is equal to N.
Yeah.
Right? So then, there exists, what should we call those integers? X and Y. You didn't want to use X there, but now you want to use it?
Oh, not X. X. Do P and Q.
P and Q. Okay, so there exist two integers, P and Q. So then, there exists P and Q in the integers such that N is equal to P plus Q. Right? That's what it means for N to be in B. If N's in B, then there's two integers such that their sum equals N, comma, and P and Q are odd. They're odd integers, right?
Yeah.
But an odd plus an odd is a,
Even.
how do you know that?
We prove it.
You proved it. we already know it's even. If it's divisible by 2, then it's, oh, because you're saying that's how I defined it up here. Then n is even, which gives us 2 divides n, right? That's the definition of even, 2 divides it, which then gives us n is in A. Okay, that's better. So we just barely showed anything in B is also in A. If it's in B, it's a sum of 2 odds. If it's a sum of 2 odds, it's even. If it's even, it's in A. Good?
Yeah.
Yeah.
Now we need to do the second part. We need to show that anything in A is also in B, and then we're done. So, 5. What are we going to use so I don't confuse you?
M.
M. Let M in A. If M's in A, what do we know?
That is divisible by
Yeah. Then 2 divides M, which gives us that there exists
2 integers.
R such that, R and Z, such that M is equal to 2R, which gives us that M is equal to 2R plus 1 plus negative 1. Right?
Wait, I didn't get that.
Huh?
I didn't get that.
2 divides M. So there exists some integer R such that M is equal to 2R.
That's the definition of even.
Okay.
That's the definition of divides.
Oh,
If
yeah.
2 divides M, then 2 times some integer equals M. And then this is still just 2R.
Oh, you just wrote
Plus
it.
1 minus 1.
You just wrote it.
And I just wrote some parentheses because what's this?
Odd.
What's this?
Also odd.
Odd. It's an odd and an odd.
Why did you write the plus negative 1 then?
Why did I write
Oh,
plus?
it's an odd plus an odd.
Yeah!
Okay, I got you.
7, therefore, M is in. M is in B. Because it can be expressed as a sum of 2 odds. And any integer that can be expressed as a sum of 2 odds is in B. That's the definition of B. We good? Pretty understandable, nice and easy. Okay, moving on. Definition of a subset. We say set A is a subset of B, and we write it like this: A is a subset of B, provided that every element in A is in B. If everything in A is in B, then A is a subset of B. For those of you with like logic, A is a subset of B is logically equivalent to X in A implies X is in B. Now this is a symbol I told you you're going to get confused with this symbol. And you're gonna. So let's watch it happen. Is a set 1, 2 a subset of 1, 2, 3?
Yes.
Yeah.
You sure?
Yeah.
Yeah. Is everything in this set? Yeah, then we're good. Alright, let's look at this one. Is a set 1, 2 a subset of the set containing 1, 2, and 3?
No.
No. 1's in here, 1's not in here. 2's in here, 2's not in here. Right? Next, is the set 1, 2 a subset of the set 1, 2?
Yeah.
Yeah.
It's not smaller, right? It has to be smaller to be a subset. That's what the definition says. Where were we? We say the set A is a subset of B, provided that every element in A is in B.
So it's a
Oh, so it is. So nothing about smaller in there. So yeah, that's a perfectly valid subset. Which one wasn't? This one. That's not a subset. Don't get confused by that. But that one was in there. It was in there, not a subset. The set 1, 2 is in this set. It's not a subset of the set. Right? Okay. Ready to move over. Let me turn our camera.
See, I like learning it. I just don't do it.
What did you say?
I said I like learning it, but I don't like doing homework.
You like learning it, but you don't like doing the homework?
Yeah.
Oh, we'll just leave it like that. All right,
Makes no sense.
let's do a quick proof then. So for set A, x is in A if and only if the set containing x is a subset of A. Okay? So this is an if and only if proof, so we need to do it two ways. We need to show that if x is in A, then the set containing x is a subset of A. And then we need to show that if the set containing x is a subset of A, then x is in A. And then we're done. Right?
Yeah.
So, 1, let A be a set. Now, which way should we prove first? Let's show x in A implies the set containing x is a subset of A. So, first I'm going to show this way, 2. We'll just get it all in one go. We won't separate that. So we'll just start from the beginning. We'll start showing this way. We'll just say 1, let A be a set, comma, and let x in A. 2. Then, I don't even know how to say this any simpler. Then, x is a subset of A. How do I add explanation to that? Then, since x in x implies x is in A, then the set containing x is a subset of A. Is everything in there in A? Yeah, by definition, x is in A. Right? Pretty trivial.
Yeah.
So simple, it's almost like what do you use other than just stating it?
Yeah.
Good. If it feels that simple, that's good. Okay, so now let's do the other way. Let A be a set such that x is in, not in, is a subset of A. Or then x is in A. Right? That's what it means to be a subset.
Yeah.
Everything in there is in there. And we're done.
Why is that even needed to be proved?
Exactly. In case there's any confusion, just to hammer home the difference between this symbol and this symbol so that you don't get confused later. So overkill to make sure you completely understand those symbols. I think that's the point. Maybe the author says something different. Okay, moving on. Pythagorean triples. A list of 3 integers, A, B, C. Now we're talking about lists, not sets. A list of 3 integers, A, B, C, is called a Pythagorean triple, provided that A squared plus B squared equals C squared. So here's an example of a Pythagorean triple. 3, 4, 5. 3 squared plus 4 squared equals 5 squared. Right?
Yeah.
No.
What's 3 squared?
Oh. Wait. 3 squared is 9.
What's 4 squared?
16.
9 plus 16?
Probably 25.
9 plus 16?
9 plus 16. 25.
25.
That's what I said.
Alright, let's try this one. What's 5 squared?
25.
What's 12 squared?
144.
144 plus 25?
Square, 13 to the power 2.
169. Yeah. And then 6, 8, 10. 36 plus 64 is 100. Right? So there's some examples of Pythagorean triples. Now we're going to do a proof that sounds really messy, but is actually pretty simple. So first let's wrap our head around what we're trying to prove. That's harder than the actual proof. So let P be the set of all Pythagorean triples. So it's the set of all ordered triples A, B, C, where A, B, and C are integers, and A squared plus B squared equals C squared. So P is that set. And let T be the set of all ordered triples P, Q, R, such that P is equal to x squared minus y squared, Q is equal to 2xy, and R is equal to x squared plus y squared for any 2 integers xy. Yeah, it's a lot. So pick two integers, x and y. Give me any.
2, 3.
2, 3. So we'll say x equal 2, y equal 3. Then the triple, oh, I guess, do these just have to be integers? Yeah, this should work. But let's keep it positive, so we'll do 3, 2. So then p is equal to x squared minus y squared. So 9 minus 3 is, or 9 minus 4 is 5. That's what p is. Q is equal to 2 times x times y. So that's going to be 12. And then r is equal to 3 squared plus 4 squared, which is
You mean it'd be
13. Or 3 squared plus 2 squared. 5, 12, 13. So notice that was a Pythagorean triple. And it was also in this set T. We're proving that every Pythagorean triple is also in this set T. In other words, every Pythagorean triple, for every Pythagorean triple, you can find an x and a y, such that x squared minus y squared gives you the first number, 2xy gives you the second number, and x squared plus y squared gives you the third number. Make sense? Seems completely out of the blue, completely unmotivated. This is a more of a number theory proof, but the author introduces it, so we'll use it.
Wait, your symbol over there says T is a subset of P, but then you said every.
I said it backwards. Correct. T is a subset of P, not P is a subset of T. Any xy that satisfies that, it's going to turn out it's a Pythagorean triple. It gives a Pythagorean triple. So you're right, I said that backwards.
So
Which is
you're
why
trying to
when we
explain-
picked two random xy's, it worked.
I'm trying to explain that everything in T is in P.
Yes, everything in T is in P. So I'm going to grab something out of T and show that implies it's also in P. Make sense? Okay. So, I don't know what, we'll just use PQR again. Let PQR in T. So we're grabbing one thing out of T. We're calling it PQR. 2. If PQR is in T, what does that mean? It means that there exists some x and y. There exist integers x and y such that p is equal to this, q is equal to this, and r is equal to this. Right?
Yeah.
So then, there exists x, y, and z such that p is equal to x squared minus y squared. Q is equal to 2xy. And r is equal to x squared plus y squared. Right? Now, how are we going to show that this thing's in P? We need to show that this is in P. How do we do that? We need to show it's a Pythagorean triple. Or in other words, we need to show that p squared plus q squared equals r squared. And we're done.
Yeah.
Right? So that's what I need to figure out. I need to figure out what p squared plus q squared is, make sure it's r squared, and we're good. We know what p is, so we can figure out p squared. We know what q is, so we can figure out q squared. We know what r is, so we can figure out if in the end it's r squared.
Okay.
That's all we're going to do. So, then p squared plus q squared is equal to, let's figure it out. What's p squared?
X squared minus y squared twice.
X squared minus y squared twice, that's going to give us x to the 4 minus 2x squared y squared plus y to the 4, right? Do we know how to do that, or was that too much? Simpler version. If I have a, let's see, we had minus a minus b squared. What is that? That's going to be a times a plus a times negative b plus negative b times a plus negative b times negative b, right? So let's do it all. A times a is a squared. A times negative b is negative ab. Negative b times a is negative ab. Negative b times b is positive b squared. minus 2ab plus b squared. Exact same thing. We've got a squared minus 2ab plus b squared. You follow that? Pretty common way to think about it. Anyways, so this was p squared, now we need q squared. Which is just, what's q squared?
4x squared y squared.
4x squared y squared. Okay. 4x squared y squared. Now notice we have a common term.
X squared, Y squared.
X squared, y squared, x squared, y squared. So when we add it all up, we're going to get x to the 4 plus 2x squared, y squared plus y to the 4. Everyone follow that? I'm combining these 4 x squared, y squareds with these negative 2 x squared, y squareds, leaving me a total of 2 x squared, y squared.
Yeah.
We're good?
Yeah.
Okay. Which, now we can just factor this, is the same thing as x squared plus y squared squared. When you see this, if we have a plus b squared, that's going to be a squared plus 2ab plus b squared. Same thing. A squared plus 2ab plus b squared is the same thing as a plus b squared. Follow that?
Yeah.
Therefore, it's in P. Therefore, PQR, yeah, PQR is in P. No, we're not showing that they're equal.
Oh.
We are showing that one's a subset of the other. Proving that they're equal, I think we need some number theory to go the other way. Anyways, there's that proof. Okay. So now we're going to move on to counting subsets. We want to know how many subsets can we get. Sorry, we're shifting gears suddenly. That's the end of that proof. Moving to a completely new topic. The new topic is counting how many subsets you can get from a particular set. So here's a set 1, 2, 3. What are all the subsets I can get from this set 1, 2, 3?
Like 6.
Like 6, maybe 7, probably even 8. So let's write them out. First off, is this a subset?
Yes.
The set containing nothing? Is everything in there in there?
Yes. There's not nothing there.
What's in this set?
Nothing.
Nothing.
There's not nothing there.
Is there anything in here that's not in here?
Yeah, nothing. Wait.
Is there anything? Yeah, nothing. Yeah, the not of anything. Okay, yes, this is a subset. And we use this empty set so much, so we call this an empty set, the set containing nothing. We use this set so much that we have a special symbol for it, which is this, the empty set. So I don't like drawing squiggly braces over and over again, so I'm going to use this for the empty set. It's a squiggly braces with nothing between them. So this is a subset of that. What else is a subset?
1.
The set containing 1, the set containing 2, the set containing 3, the set containing 1, 2, the set containing 2, 3, the set containing 1, 3,
Then can't you go backwards?
and the set containing 1, 2, 3. That's all.
Okay.
How many are there?
8.
There's 8, right?
Yeah.
Okay. How many subsets can I get of this set? Anyone want to take a guess?
10.
More than 10.
16.
16. How'd you get that? Just a random guess? All right. Did anyone have a justification for 16? So here's the way that we think about it. For each subset, I have the choice. Do I include 1? Yes or no? Well, let's make this a list because we'll make a list for each subset. For each subset, I could make a list of y's or n's, yes, yes, yes. So yes, no, yes, yes means I include 1, I don't include 2, I include 3, and I include 4. So this would be the same thing as, this would be representing the set 1, 3, 4. You with me?
Yeah.
If I did n, what set is this representing? The empty set. In that case, it's the empty set. We're saying we didn't include any of the 4 elements. So a y here means include 1. An n here means don't include 1. This means include 2 or don't include 2. This means include 3 or don't include 3. This means include 4 or don't include 4. So I have include 1, yes or no, 2 options. Include 2, yes or no, 2 options. Include 3, yes or no, 2 options. Include 4, yes or no, 2 options. So I have 2 times 2 times 2 times 2, or
2 to the power 4.
2 to the 4, which is 16 options. Just like up here, I had, do I include 1? Do I include 2? Do I include 3? 2 times 2 times 2, 8 options.
Okay.
Make sense? Because now we're going to do a proof that it is in fact the case, but it's going to be a counting proof. So you remember my last counting proof, how I got a picture for you guys and made sure the picture made sense before my proof talked about the picture? Similar thing is going to happen here. So here's high level the way that the proof's going to work. We're going to look at any set that has n objects. So here's a set: circle, triangle, star, 13, house. Right?
Yeah.
How many objects are in this set? There's 5 objects in this set, so n is equal to 5 in this case. So we know that there's how many possible subsets I can make of this?
32. 10 to the power 5. I mean.
Whoa.
2 to the power 5.
2 to the power of 5. We either decide, do we include circle, yes or no? Do we include triangle, yes or no? So 2 options, 2 options, 2 to the 5 options. Okay? So here's what I'm going to do in my proof. I'm going to say for any n size set, in this case n is 5, we can relabel the objects in the set as A1, A2, A3, A4, all the way up to AN, in this case A5. So I'm going to relabel them this way so that I can talk about them, because notice here, in general, I don't know what's in the set. Anything could be in there. Right? So I'm going to arbitrarily pick one and call it A1. I'm going to arbitrarily pick one and call it A2. And I'm just going to randomly pick out all the elements, calling them by this symbol. That way I can reference them from here on out. You with me?
Yeah.
And then I'm going to say, notice that we can view it then as an n-element list. 1, 2, 3, 4, 5. For each subset, we can view each subset as an n-element list, where we decide yes or no, do I include A1? Do I include A1, yes or no? Maybe yes, and then no, and then yes, and then yes, and then no. So for this list, what set is this list representing?
A1, A3, A4.
That's what's representing in terms of A's, but going back to our original list, this is representing the list circle, star, 13. So I'm going to say each of my lists, I'm going to take them, relabel them this way to make a list for each possible subset. We're going to count all the subsets. It's going to be 2 to the n. That's how the proof's going to work. Good?
But why do you
Yeah.
really need to relabel?
So just so I can talk about them, you'll see where I talk about the. I'm going to say in the kth position, look at A sub k. So in the 3rd position, look at A sub 3. If it's in the set, put a yes. If it's not in the set, put a no. That's why I need a label so I can talk about it that way. Okay. I'm not sure how far I got in the proof. I don't think I finished, so we'll fill in the blanks as we go. Okay, so let A be a set. Then if it has, then it has how many subsets? I didn't want to give you the answer. It has 2 to the,
2 to the power 5.
2 to the power 5.
well, in general, it has 2 to the n, but n is the size of A, remember?
Yep.
So 2 to the size of A. If A has n elements, then it's 2 to the n. But in general, it's just going to be 2 to the size of A.
Okay.
Is everyone okay with that notation, or is that just too weird? We're good? All right. That's a big smile. Okay. Let A be a finite set, and let n be the size of A. Good so far? Relabel the n elements of A as A1, A2, all the way to AN. Good?
Yeah.
To each subset B of A, we can associate an n-element list of the words yes or no. How are we going to do that? For each subset list, it owns the list, we include yes if the kth position, we include yes, in the kth position. I just read that wrong. In the kth position of the list, if and only if A sub k is in the subset. Right? For each subset list, we include yes in the kth position. In our case, we just did y instead of yes. So we include yes in the kth position of the list if and only if A sub k is in the subset.
Yeah.
So we're making a list for a subset. I put yes in the third position only if A sub 3 or star is in the set.
Yeah.
Make sense? Then, maybe no point even continue writing this because I can talk faster than I can write. It's just explaining. So, we know that we can create a list for each subset this way. Therefore, all the lists we can possibly create is all the subsets we can possibly create. Right?
Yeah.
Therefore, it's just counting the lists. We know how to count an n-element list with 2 options for each element. It's 2 to the n. Therefore, the number of subsets we can make of A is 2 to the n. N was the size of A, so it's 2 to the size of A. You feel like you understand that?
Yeah.
You might feel fuzzy on how would I prove it, but do you understand it?
Yeah.
Because that's the part that matters. These counting proofs, they feel weird when you first come across them, and honestly, I don't know the trick to just get comfortable with them. It just feels like all you're doing is explaining high-level intuition a lot of the time, but we'll do more of them that have other ways of counting. So let's see. Lastly, the power set. The power set. We'll come back over here since I got erased anyway, so that my camera's not on a weird angle. I don't want to turn. Can you move the desk? So the last concept we need to talk about is the power set. The power set of a set is the set of all possible subsets. So we'll make this make more sense. And then I'll write down the exact definition he gives, but here's what it is intuitively. If I have the set 1, 2, keep it small, then we use a fancy P to signify the power set. So we have a P something like this. The power set of the set 1, 2 is equal to the set containing all possible subsets.
Okay.
So it contains the empty set, it contains the set containing 1, it contains the set containing 2, it contains the set containing 1, 2. Right? And notice that the size of the power set, so the size of the power set of A is going to be 2 to the size of A.
Yeah.
We just barely proved that 2 to the size of A, this is how many subsets there are, possible subsets there are of A. P of A is the set of all possible subsets. So in this case, P of 1, 2 was 2 to the 2, or 4 in size. Making sense?
Yeah.
No? You're good with that, the definition of a power set?
Yeah.
Okay, so now we're saying, how many elements are in the power set of a given set? How many elements were in this set?
4.
4, right? What did we just prove over here? We proved if A is a set, then it has this many possible subsets,
Okay.
right? So if A is a set, and P of A is all its possible subsets, then how many possible subsets does it have? 2 to the size of A.
Okay, but write that as, give A a number. Give A a set.
So when A was this one,
Okay.
then it was 2 to the 2.
2, 2. Okay.
You see it?
Because
Let's-
there's 1 and 2.
Because there's 2 elements in here.
So that 2 is.
So in this case, it was A, right here we did, A was 1, 2. What's the size of this set?
2.
2, so put 2 up there. So size of 2, not, or so 2, not size of 2, right? But in general, this is A, and this is 2 to the A. Good? Notice right here, where did we write those? Oh, we erased it, didn't we? All the subsets of 1, 2, 3. So, but you remember there were 8 of them, right? So when we did the power set of 1, 2, 3, 3, when we did the power set of that, then we listed out, you remember 8 elements, right? You remember that?
Yeah.
Let's list them out again. What's the power set equal to? This is going to be the set containing all the possible subsets of this. We can have the empty set, we can have the set containing 1, we can have the set containing 2, we can have the set containing 3, 3.
1, 2,
We can have the set containing 1 and 2,
2, 3.
we can have the set containing 2 and 3, we can have the set containing 1 and 3, 3, and we can have the set containing 1, 2, and 3, right?
Yeah.
So the power set of the set 1, 2, 3 is the set of all the possible subsets of 1, 2, 3. Take any element inside this set, and it's a subset of this set. Good? So the size of this is the same as the size of this. But what is the size of this? It's 8 in this case. So as a general rule, which is the same thing as 2 to the 3, right?
Yeah.
So as a general rule, the size of the power set of A is equal to 2 to the size of A. In this case, A was a 3-element set, so the size of its power set was 2 to the 3. Make sense? And so if this was a 4-element set, we would have drawn out 16 sets. If this was a 5-element set, we would have drawn out 32. If this was a 10-element set, we would have drawn out 1024. We'd be busy. Okay, so that's a power set. Let's see. Let's get the exact definition. Let A be a set. The power set of A is a set of all subsets. I think we've already got that. Last piece of notation. This is one of the weirdest, most confusing pieces of notation you'll see in this class. So, sometimes, instead of writing the power set of A this way, we instead write it as 2 to the A. 2 to a set. This is 2 with a set up here. Not 2 to a number. We're not talking about a number. We're talking about power set. For this, so power set of A is a set of all possible subsets. Another way we sometimes write that is 2 to the A. So in other words, if you were to see 2 to the 1, 2, what is this equal to? This is equal to the set containing the empty set, the set containing 1, the set containing 2, and the set containing 1, 2. So when you have 2 to a set, it's talking about the power set. This is kind of weird notation. I'll always try to do it this way, but you might have like homework problems that ask you to figure out what this is. And that might seem kind of weird to you to
So
figure
if
out.
it asks us that, then we should give them that.
Yeah, it says find 2 to the 1, 2. Here's your answer. Make sense? And I don't want to go through explaining why that notation's used, but I agree it's weird. It makes more sense when you give numbers their set theoretical definition. Then it makes more sense. And I think that that finishes it. So, does someone have their syllabus readily available? I think that's all we were supposed to cover today. That's the end of section 10.
I think we're supposed to cover section.
I thought we were supposed to go on to 11.
Go on to 11.
11.1 to 7.
9, 10, and 11. Yep. All right, so I guess we're doing another section. Oh, that's why, because the next section is just quantifiers, which will be real quick. So for all of those of you in logic, you're already going to know this. I think I've already been using these quantifiers, but we'll go over them. So we have two quantifiers that we use all the time. We have the universal quantifier, which is the for all, and we have the existential quantifier, which is the there exists. Okay? I've already been using these symbols, right?
Yeah.
Not this one?
Not that one, but there it is.
So let's give an example of a statement using the for all. For all x in the natural numbers, comma, x is greater than or equal to 0. True or false?
True.
True. Let's try this one. For all x in...
So it doesn't really like you could just say x.
Well, no. I can't just say x in n, x is greater than or equal to 0. I can say if x is in n, then x is greater than or equal to 0. But this is saying every x in n is greater than or equal to 0. Or for each x in the natural numbers, x is greater than or equal to 0 is a lot of ways to say it. So let's try another one. For all x in z, comma, there exists y in z such that x plus y is equal to 0. True or false?
True.
Is it true that for every integer, I can find an integer such that their sum is 0?
Yes.
Yes. For any x for every x, there is a y such that their sum equals 0. What is that special y? Negative x. Right? Let's switch it up. Or there exists an integer x such that for every other integer or for all integers y, x plus y equals 0. Is that true?
No.
Is it true that there exists an integer x so that for all integers y, their sum is equal to 0?
Yeah.
Yeah.
It's just the same thing backwards.
No, this one is false. There is not an integer x such that for every y, when I add them together, I get 0.
Is there?
But what about the negatives?
So give me the x.
Oh, you're saying for just one.
Yeah. Does there exist an x
Just one.
so that for every y, when I add y to it, I get 0?
I see.
Okay.
Let's go back to the first case that we had. For every x, there exists a y such that their sum is 0. That one's true.
Yeah.
For every integer, there exists a negative of that integer, is basically what this is saying. But there does not exist an integer such that we can add anything to it and still get 0. Right? Let's do another one. Let's go back to our broken one and see a case where it worked. So in this case, it's false. There exists x such that for all y, this is true? No. But if we switch this to a times, what about that? Does there exist an integer so that for all integers, their product is always 0?
0.
Yeah, 0 is that magic x that makes this true. Make sense? And then negating these. Trying to think about how to do this without getting into logic notation. Maybe we can just do it. If I say that there exists some x such that, hopefully these parentheses don't throw you off, such that some statement about x is true, then that is the same thing as saying it is not the case that for all x, some statement about x is not true. So let me help this appeal to your intuition, how these are both saying the same thing. If I say there exists a swan such that that swan is black. So the statement about x is it's black. So I'm saying there exists a swan such that a swan is black.
Okay.
Or there exists a black swan. Another way to say this is the same thing as saying it is not the case that for every swan, a swan is not black. If there is a black swan, then it is not the case that every swan is not black.
Okay.
Is that kind of clicking? And vice versa, if we say that for all x, some statement about x, for every swan, the swan is white, is logically equivalent to, it is not the case that there exists some swan such that that swan is not white. If for every swan, that swan is white, that's logically equivalent to, there does not exist some swan such that the swan is not white. Every swan is white, there is no non-white swan. You see how those are saying the same thing?
Yes.
So here's the rule. If you have not some quantifier, there exists x, s of x, and I want to distribute the not, I switch this from a there exists to a for all and put the not in here. So not there exists a white swan is the same thing as for all swans, that swan is not white. If there does not exist white swan, then every swan is not white.
Okay.
So when you distribute the not, it switches your quantifier from existential to universal, and you put the not next to the statement that you're talking about. Make sense? Let's do it in reverse. If we're saying not for all, that's the same thing as exists not. So let's say it with words. Not every swan is a white swan, means there exists a swan that's not white. You seeing it? So universal quantifier, existential quantifier. We go back and forth between them all the time, not make a switch them. That's all there is to quantifiers. Any questions about quantifiers? Any of you guys who are already comfortable with quantifiers have any examples that you found helpful or anything like that?
Going over it.
Yeah.
Just over and over and over again? Just more and more sentences? All right, let's pick some sentences, we'll symbolize them, and then we'll do the nots of them. So give me a sentence with an existential quantifier in it. Talk.
For every Laura, she has.
Don't make it that convoluted, just say a normal sentence. Roses are red. Right? Roses are red. What are we saying with this sentence if we want to symbolize it with quantifiers? We're saying for every rose,
It is red.
red applies to that rose. Right? So now what if we want to say not roses are red? What if we want to say this statement is false? What are we saying? We're saying that there exists a rose that is not red.
Yeah.
Right? Maybe start this with all to help the language a little bit. All roses are red means for every rose, that rose is red. Now if we want to say not all roses are red, or the statement is not true, then what does that mean? That means we're trying to distribute a not on this now. So that's going to be there exists x, not Rx. Or in other words, there exists a rose that is not red. Would be the negation of this. Is that helping?
Yeah.
So we good, you think? let's write down just a bunch of mathematical statements. I think he has like a list of them that use these things. And then we can just go through true or false, true or false, true or false. He has them spread out. Jeez, he's really making it hard for me to just write down the list. Okay, for all x there is this way. Oh, we did that one. You don't have any new ones? Oh, here we go. This is what I was remembering. So I'm going to write down, you're going to tell me true or false. For all x, it's assumed that we're talking about in numbers, in the real numbers. So for every real number, does there exist a real number such that their sum is 0?
Yeah.
So this is, you're saying this one's true? All right, next one. Oh, that wasn't the first one. This was the first one. For all x, for all y, x plus y equals 0.
False.
False. Yeah. It's not the case that the sum of any two numbers is 0.
Yeah.
Okay. Let's see, the next one is, there exists x for all y, x plus y equals 0.
False.
False?
Yes.
Yeah. There is no magic integer such that whenever you add to it, you get 0. It's not a thing. And then he does, oh, I see the pattern next to me. Then he just does there exists, there exists.
Which is true.
And then I think he repeats all 4 of these with just multiplication. So let me set this down. Is this one true or false? Oh, sorry. Did we do this one?
Yeah,
Yes.
it's false.
False. Okay, now this one.
True.
True.
True? You're telling me that there exist two integers such that their sum is 0?
Yeah.
Yeah.
What are they?
1 and 1.
Yeah. Tons of them. All right, now let's repeat, do the same process, except for now we're going to replace all the pluses with times. So now we're doing times, 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 times. All right, first one. For all x, for all y, x times y is 0?
False.
False. For all x, there exists a y such that their product is 0?
True. Yeah.
True. For every x, there does exist a y. In this case, you can just pick 0 every time, such that the product is 0. There exists an x such that for all y, the product is 0? True. 0 again. There exists an x and a y such that the product is 0?
True.
False.
It's true.
It's true. All right. So there's a bunch of exercises using these quantifiers over and over again. So just quantifiers. I don't know, pretty weird when you first get used to them, but once you get used to them, they just become a natural part of your language almost. You don't even think that much about it anymore. So that's it. Any other questions about quantifiers?
Yes.
Oh, questions on homework? Yeah, so now we'll turn off the recording because I don't think you'll care. And